last time we talked about torque and what it was and how it was a force, a distance from a center of rotation. Today we're going to figure out what happens when you apply torques on things. They angularly accelerate. You apply a torque on that bolt, and this bolt is going to angularly accelerate in that direction. And it's going to do that proportional to its moment of inertia. So this is just like F equals ma, where mass resists linear accelerations. Here you have moment of inertia to resist angular accelerations. Let's do a quick example of this. So here we have Pac-Person from our favorite 1980s video games. And unfortunately, this person is on this trapdoor, which is going to fall out. So first we're going to look at the torque caused. So we want to find angular acceleration. We know that that is torque over the moment of inertia of whatever is going to angularly accelerate. In this case, that rod, which the rod about the end is 1/3 ml squared. So the torque is Rf sine theta, where the torque right here is caused by the force of gravity, the weight of that person standing on the trapdoor. And this would be your R. In this case, it would be 0.7 meters. So when we apply our numbers into here, 0.7 meters, 80 kilogram person, this is the weight of said person, force of gravity acting on the person, over the moment of inertia, we find out that the angular acceleration is negative 28.6 radians per second, where again, the negative sign just means that it is rotating clockwise. And that worked out pretty nice. But now we're going to talk about the center of mass and the force of gravity. So we're going to look at weight again, and I've got this rod here. And if we'll notice, there's weight acting on the sides. So each of this little piece over here and this little piece over here, if it's a uniformly dense rod, have the same mass. And gravity acts on both of them. The force of gravity acts on both of them. Okay, well, the torque from this one and this one is going to negate one another, because this causes rotation this way about the center, and this one will cause rotation this way. So let's go inwards. And oh, look, the torque from this piece and this piece also cancels out. And we find out if we keep doing this, we get that the entire mass of this rod is right here, in the center of mass. Now, why is this useful? Because we can pretend that the entire force of gravity acts at the center of mass on that rod. So the center of mass is also where you can draw an arrow for the gravitational force. In this case, now I put this on a pivot, so it also experiences the normal force pointing upward. So this just looks like a sum of forces in the y direction equals MAY. So in this case, not accelerating, but we would have N minus mg, which is exactly what we've done before, except now we have a place to put where the arrow comes from, and that arrow comes from the center of mass. This is going to be useful coming up. We're not going to talk about it much anymore, but please ask if you have questions. I will see you in class.